In this video, we are looking at heterocyclic aromatic compounds and Huckle's rule. And if you haven't seen our introductory videos, then you can check our playlist for them. We have introduction on what aromatic compounds is. We talk about Huckle's rule, so you can check it out. And so we did mention that for a compound to be aromatic, we need to look out for some things. The first thing is, let's find out if that compound is cyclic. And then secondly, we need to find out if that compound is conjugation. And the third is to look out for resonance. And then we also talk about Huckle's rule. And when we were talking about Huckle's rule, we mentioned that anytime we have 4n plus 2 pi electrons, then that compound is likely to be aromatic. And then if we have 4n pi electrons, then we consider that compound is anti-aromatic. Now, what if we have odd number of pi electrons? So let's say odd number of pi electrons. Then we know directly that that compound is non-aromatic. Alright, so this basically summarizes what Huckle's rules talks about. And so for now, we are looking at this heterocyclic compound, and let's look at what PYRROLE is. PYRROLE is a chemical compound and it's 5-membered ring. So I'm going to draw the structure here and then we'll have a look at it. So PYRROLE is like this. We have, remember that I said it's 5 members, so nitrogen here, and then we have this place double bond. The nitrogen has a lone pair on it. Alright, so what is it about PYRROLE? Can we say this compound is aromatic or not aromatic? Alright, the first thing we have to take note of is that the lone pair on the nitrogen, this lone pair on the nitrogen, is part of the aromatic sextet. So this lone pair is part of the aromatic sextet, which means that, and also before we go on, remember that we mentioned that in aromatic compounds, most of the bonds we see the carbons are sp2 hybridized. They're sp2 hybridized. And so if we count the number of pi electrons here, we see that we have 6 pi electrons here. Okay, so you may say that we have only 2 pi bonds here. How can we have 6 pi electrons? Just like I mentioned, this lone pair is part of the aromatic sextet, in that we have this nitrogen to be sp2 hybridized. If it is sp2 hybridized, then it means that we have the lone pair in the p orbital. So if we take nitrogen, let's say nitrogen, let's look at the hybridization of nitrogen. Nitrogen, remember, is 7. So we take nitrogen, the first orbital, 1s will take 2, and then the 2s will also take 2, as well as the sp, this p orbital is taking 3. So let's focus on the 2s orbital. So this is our s orbital. It has this double spin. Now when we take this, we have the ps who's going to be having 1 electron, py, and the pz. So when a hybridization takes place, if nitrogen is hybridized, we are going to have sp2 orbitals. And so what will happen is we'll have sp2 orbitals. One of these electrons in the 2s orbital here will move into one of these p orbitals. And so we have this sp2 orbitals. We're just going to be having these spins, and then we'll now have a p orbital. So let's say probably pz orbital, which is going to be having two spins, that is two electrons in there. So we can say that these three orbitals, these three hybrid orbitals sp2 are used in the bonding, and then we have this p orbitals having two electrons in it, and that is what this electron here, this lone pair of electron is. And so because we know that pi bonds they are formed by the overlapping of p orbitals, we can count these two electrons as part of the aromatic pi electrons. Okay, so if you check that out, you can find out that this compound here becomes conjugated, and so you can have these electrons combining with an electron here to form a double bond here, and so we're going to be having the alternation of these electrons in here. So we can say that pyrrole is aromatic. Pyrrole is aromatic. Now let's look at another example. Let's look at pyridine. Pyridine, we all know pyridine is very popular. So pyridine is a cis-membered ring, but then we have nitrogen in there. So this is pyridine. This is pyridine. Alright, so what about pyridine? Can we say pyridine is aromatic or is non-aromatic? Now, before we do that, we need to count the number of pi electrons. So each pi bond offers two electrons. So we have six pi electrons in the 6 pi electrons. Alright, and is it conjugated? Emphatically yes, it is conjugated. These bonds can be alternating, so it is conjugated. It is conjugated. But then what is it about this pyridine that is different from what we just looked at about the pyrrole? Alright, now we have to take note that because the nitrogen is doubly bonded, it contributes one pi electron to form the double bond. Over here, it contributes one pi electron to form the double bond. So we can say that the lone pair on nitrogen is not part of the aromatic system. It's not part of the aromatic system. How? Again, we have to look at the hybridization of nitrogen in here. We have to look at the hybridization of nitrogen. So if we take nitrogen, we said nitrogen is 7, right? So if we take nitrogen, we look at the hybridization. We still have one S having two electrons, our 2S having two, and our 2P having three. And so let's draw that box again with the opposite spins, then the p orbitals. Alright, so hybridization, how is it going to be like? So let's look at this. We know that aromatic compounds are sp2 hybridized. So if we have the sp2 hybridization, what is going to happen is we have these three orbitals. We'll have a spin here, but then when it comes to the last orbital, we have an opposite spin. So we have 4 electrons involved in this sp2 hybridized. So we can say that this lone pair on nitrogen here is in an sp2 hybridized orbital, and so we don't count it when we are counting the pi electrons in this compound. And so what happens to where do we get electron to form the pi bond here? There's going to be one orbital of p here, one orbital of p, which is going to be having one electron there, and this one electron is what combines with the carbon here to form this double bond. So we have 6 pi electrons in pyridine. We have 6 pi electrons in pyridine, and we can say that it is conjugated. It is conjugated, and so pyridine is what aromatic. It is aromatic. You know, there are some common questions that they are likely to ask you. They can ask you, they can ask you, why is it now that why do we have pyro not being basic, but pyridine is basic? But pyridine is basic. All right, it is really simple. When we talk about Lewis base, it's all about the donation of electrons. It's about the donation of electrons. Now, if you go back, can we go back there? Let's go back there. If you look at pyrrole over here, we have the lone pair here contributing to the total pi electrons in the compound. But when we come to pyridine, we found out that this lone pair is not contributing to form any bonds, or it's not contributing to make the compound stable through aromaticity, but it is just there open in an sp2 hybridized. So this lone pair can be easily given out, and that makes pyridine to be a Lewis base. That makes it to be a Lewis base. So I can expatiate this a little bit further. So let's look at this structure once again. So this is our nitrogen. Oops, don't mind my drawing. Okay, you let's clean it and draw it even better. I have an eraser here. Okay, just forget about that. Um, all right, I just zoom that up more than normal, so we need to get rid of that. Okay, so let's look at this structure. There is a nitrogen. My nitrogen looks a lot like H, so let's make it nitrogen, of course. So if you look at the orbital system, we have this orbital here. I'm drawing the p orbital. So all right, so what is happening here, we have this p orbital electrons in each of these p orbitals. So we have an electron here. Don't do that. We have electron here, electron here, electron here, electron here, and also an electron here. Okay, so before we form those bonds, those double bonds, what actually happening is we have we'll have two of these each combining to give us. So if you take the nitrogen, we have these two that are going to combine to give us a pi bond, and then we also have this overlapping to give us a pi bond, as well as this overlapping to give us a pi bond. But then we have another orbital here with these two electrons in it. So basically we found out that it is the overlapping of this p orbital from nitrogen, which is having one electron in the p orbital overlapping with that of carbon to form this double bond here. And so the lone pair has nothing to do with the p orbitals, but it is found in the sp2, in the sp2 hybridized orbital. All right, so now I think we have to look at another example. So okay, let me check this. All right, now let's look at another example. Let's look at THIOPHENE. Okay, so we are looking at THIOPHENE. THIOPHENE is a five-membered ring, but anytime we hear about thio, then we know that we have sulfur in there. We know that we have sulfur in there. So let's draw our thiophene. This is our sulfur. Oops, my hair is really, whoa. So we have our thiophene, and sulfur have this lone pairs on it. It has two lone pairs on it, and we have our double bonds here and here. Okay, so we are trying to find out if this compound is aromatic or not aromatic. So we know that it is cyclic. Of course, it's cyclic. How many pi electrons do we have there? Okay, we have 6 pi electrons because this is 1. This bond, this pi bond is giving us what? 2 electrons. This is giving us 2. And then we have these 2 lone pairs. Don't worry about this. We'll come back to this later. So we have 6 pi electrons. We have 6 pi electrons, and it is conjugated. It is conjugated. It is conjugated. And so we can boldly say that our thiophene is aromatic. Now, can you tell why this is aromatic from what we did earlier? If you want to try it, you can just pause the video and then do the hybridization and find out if sulfur is aromatic or not aromatic. Alright, so if we draw this structure, if you draw this structure, of thiophene, and we put our N here, our S, sorry. Let me clean that. Okay, so we have our S here. Okay, so let's put our orbitals and see. Oops, don't do that to me. So we are drawing our p orbitals. Alright then, and then sulfur, that of sulfur. So if you do the hybridization, you find out that we have electrons in each of these orbitals. In each of these orbitals. Okay, so we have these two overlapping to give us a pi bond as well as these two. But then we have two lone pairs in the orbital of this sulfur, which make it to be conjugated. So anytime we have any of these breaking up and combining with one of these electrons from sulfur is going to be alternating and it's going to be conjugated. And so you find out that we have two other electrons in an sp2 hybridized orbital if you do the hybridization. And it's the same thing with furan. So let's look at furan. Furan is just a cousin of thiophene. So we have furan. The difference is we have oxygen in a 5-membered ring. My oxygen is really beautiful. So we have oxygen there, and then we have this. This furan is also aromatic because we have 6 pi electrons, which obeys Huckle's rule, and then we also have it conjugated for the same reason for which we have sulfur in the thiophene being aromatic. So once again, if you draw this, we're going to find out that we have these orbitals here, and the p orbital of oxygen is going to be having 2 electrons in it, 2 electrons, and then those of carbon is going to be having 1 each. So this will combine to give us a pi bond, as well as this combining to give us a pi bond, and then we have a lone pair on oxygen in the p orbital, so we can count it as the pi electron, because anytime we talk about pi electrons, we are talking about available electrons in the p orbital. And then we have another lone pair here, but then this one is an sp2 hybridized orbital, so we can count it as part of the pi electrons. So basically, this is what we are supposed to do today. We're talking about heterocyclic aromatic compounds and the obeying of Huckle's rule. So with all this, we can say that furan is aromatic. Aromatic. So thank you. We have come to the end of this tutorial, and watch out for the next tutorial. And we'll be having we're going to be looking at aromatic compounds and their reactions. That is talking about EAS. And don't forget to subscribe to this channel and share